Anybody have any questions from last time? um, okay, what's this class called? Good. And what topic did we just start last class? Rigid bodies. And also, so I said basically we don't know anything about general collections that can help us. In some isolated cases, there's stuff, but we're not going to dwell on it. So we're going into just talking about rigid bodies using that simplification. And I presented, rotational Newton's second law. It has a couple of quantities that I have to define. So today, I don't think we're going to get through all this, but we're going to start defining the center of mass, the moment, and I know most of these, at least, you've seen before, the moment of inertia, and the angular acceleration. And I'm actually going to start with center of mass, then go into angular acceleration moment. So center of mass. The definition of the center of mass is an integral definition. The total mass of an object times the position vector of its center of mass is equal to the integral over the whole mass of the position vector times the increment of mass. And I'll do a couple simple examples using these integrals. Usually we're not going to use those. Usually we'll be able to use simplifications for that calculation. For homogeneous materials, or let's say homogeneous bodies, which means same material everywhere. The center of mass, or let's say the position of the center of mass, is equal to the position of the centroid. The centroid is just a geometric thing defined by the total volume times the position of the centroid is equal to the integral over the volume of the position times an increment in volume. Most of the time, we won't use integrals. Usually we'll use some facts due to symmetry and the sum formula. Let's say the let's call it the discrete formula. That says the position of the center of mass times the total mass is equal to the sum over all the pieces that make up the body of the mass of that individual piece times the position vector of the ith center of mass. Okay, so we'll come back to that. Here are the symmetry facts that we're going to take advantage of. For objects in 2D, the centroid always lies along any line of symmetry. For objects in 3D, it's the same idea. The centroid always lies on any plane of symmetry. So I'll show you some examples of this. Break this up into 2D objects and 3D objects. So first, where does this object have lines of symmetry? Yeah, it has a vertical line of symmetry and a horizontal line of symmetry. So in this case, anytime you have two non-parallel lines of symmetry, they're going to cross, and where they cross in 2D is the center of mass, okay, or is the centroid. And if the thing is all one material, then that's also the center of mass. So right here then is the center of mass, and this is the symbol for center of mass. How about a circle? Where does that have lines of symmetry? Everything that goes through the center. So you could take any two you want. They all meet at the center. So the center is the centroid. Okay, how about this thing? You know what I'm trying to draw here, right? So really this has no lines of symmetry, but if you use your imagination, it has one, right? So the center of mass is somewhere on this line, okay? That's all we can figure out from symmetry in this case because there's no second one, right? But that does at least say that if our y-axis is pointing up, then finding the center of mass is just a matter of finding the y coordinate. We don't have to deal with x. We know that from symmetry. I'll keep saying centroid here. Okay, so how about 3D shapes? So the idea is the same. There's a plane of symmetry there. A plane of symmetry there. And a plane of symmetry here. And those all meet right in the middle. Those meet there. Those meet there. And so you have a centroid right there, or a center of mass right in the middle. For a sphere, Same idea. And then what do we know about this shape? Like a mushroom. Well, this has, what does this have for symmetry? Yeah, so yeah, you can find two planes of symmetry here, right? One cuts it like that. One cuts it like that. You can actually, I guess, find infinitely many, but they all of those share a line in common. So in this case, you know that the centroid falls along that line. Okay, we are also going to take advantage of a few formulas for just common shapes, and you know, almost any problem you do that isn't on a section in a book that's about that integral definition is going to be a combination of simple shapes that you can just look up the calculation for the centroid, you know, online, Wikipedia or whatever. So here are some of the known shapes. So centroids are simple shapes. For a semicircle, from symmetry, we know that the centroid is somewhere along that line. The question is how high along that line. And so from the center of the circle, the height up to the centroid, so the x centroid is due to symmetry, you know where that is. The y centroid is equal to 4/3 r over pi. And then you also, in order to use the centroid formula, the center of mass formula, you'll have to know the area of these shapes. So the area of this is half of the area of a circle. For a right triangle, there aren't any lines of symmetry here, so we need to know both of these components. So this is x bar, this is y bar. X bar is equal to, and actually, yeah, sorry, I'll write it this way. So x bar is equal to b over 3. Y bar is equal to h over 3. And the area is bh over 2. And then the last shape that you can't just purely use symmetry for that we're going to see is a parabolic spandrel. So if this is your coordinate system, the spandrel is the shaded shape. Then say this height is h, this x length is b. Then the formula for this parabola is y equals h over b x squared. X bar then is equal to 3b over 4. Y bar is equal to 3h over 10. And the area is bh over 3. Okay, so I'm going to do a couple examples using that discrete formula. Yep.
Do you allow us to use notes, or
I'll give you any formulas you need. Yeah. Mm-hmm.
on the red triangle, is the x bar and y bar measured from the right angle?
They are measured, that's right. Yeah, I mean, those are just distances. So in this case, I had a coordinate system. If I had a coordinate system here, this x bar would be negative, you know. Yeah, that's right. So it's this distance here and this distance here. Any other questions? Well, okay, that's a good question. So if you're doing a problem in 2D, it means usually that you have a plate, you know. So the thing is cylindrical, like its cross section doesn't change, you know. So, like for example, if you're using like an example of a time when you would use a circle and do a 2D rotational problem is even if this had a long length, you know, if you're calculating rotations about this axis, you can treat that as a circle. And so then your density, you know, like to get the mass, you'd have the density times the area times that length, you know. So yeah, there aren't actually 2D problems. They're just problems where the only difficult stuff happens in 2D. Okay, so I'm going to give a couple examples now of using that discrete formula. The first one we're going to do a non-homogeneous body. So say that you have a circular plate. Separated into two pieces, the top piece and the bottom piece. And say that the top piece has a density of 7,800 kilograms per cubic meter. And the bottom piece has a density, so this, we'll call this density 1. Density 2 is 750 kilograms per cubic meter. So this is steel, this one's wood. The radius of this circle is 0.1 meters. the thickness is 0.02 meters. And the question is, where's the center of mass? So what we really want is the position vector of the center of mass. And in order to come up with components for a vector, you need to define a coordinate system. And you can do this with any coordinate system you want. Some are probably simpler to, the numbers are going to come out simpler than others. Putting your coordinate system on a line of symmetry, so one axis is along a line of symmetry, is probably a good idea, but you can calculate it however. But let's, in this case, put the coordinate system here. And this is an example where I'm going to do this as a two-dimensional problem. But if you did have if you did it as a three-dimensional problem, in this case, the z-axis comes out of the page, and so the centroid in the z direction is just going to be right in the middle of that thickness, right? Okay, so the formula we're going to use is this one. The total mass times the position vector of the center of mass is equal to m1 times the position vector of the center of mass of 1 times m2 times the position vector of the center of mass of 2. And this whole thing isn't homogeneous, but each piece is homogeneous, so we can use the formula for the semicircle for each one of these to know where the centroid is. Anybody have a question about what I'm doing here? Okay, where would you imagine this center of mass is going to be? Do you have a feel for that? Somewhere in 1, yeah. So compared to the steel half, the wood half is almost not there. So it's going to be pretty close to what the centroid would, what the center of mass would be of piece 1 by itself, right? Okay, so piece 1. The position of the center of mass of 1 is equal to 0, 4 times the radius over 3 pi. So that comes out to be 0.4244 meters. The mass of piece 1 is equal to the density times the area of the semicircle times the thickness. So you get 2.45 kilograms. The second piece the position is 0. So look at, how do you use the formula in this case? So remember that formula just gave this in terms of a distance, right? A distance from the center towards the top of the circle. In this case, the circle is upside down compared to that formula. So you have to use that formula to figure out how far in the negative y direction that centroid is. Does that make sense? Okay, so in this case, we're going to have 0, -4 times the radius over 3 pi. So you get 0, -0.4244 meters. So as far as the distance from the center line of the circle to each of those individual centroids, they're exactly the same, right? The difference is going to be made by the relative masses and from that discrete formula. So the mass of the second piece is 750 times the same volume, 1/2 pi times 0.1 squared times 0.02, and you get 0.2356 kilograms. And so now put that into the discrete formula, and you get that the total mass, add up the two masses, you get 2.686 times the position of the center of mass is equal to 2.45 times the centroid of mass 1 was 0.4244 plus 0.2356 times the centroid of the second piece, negative 0.4244. Now solve for the position of the center of mass, and you get positive 0.35. So if this is the center of mass of 1, and this is the much more massive piece, and this is the center of mass of 2, the total center of mass is about here. Okay. Any questions about that? Okay, notice this discrete formula also works with subtraction. Okay, when you're, so you have a question?
Yeah, so this means that the center of mass is outside the body. Their radius was only 0.1. So this puts it well above the
Our radius, because I didn't do that. Yeah, what did I do? Something went wrong with my calculation there, didn't it? Yeah, that doesn't make any sense. I did not divide by pi, I'll bet. So what's 0.4244 divided by pi? No, that's not true. Sorry, could you just calculate? So 4 times 0.1, so 0.4 divided by 3 pi. Yeah, thanks. That doesn't make any sense. So wait, that 0.4 divided by 3. Oh, okay. Oh, okay. Okay. Well, good. That makes the fixing this easy. Okay. So my drawing that I did of where the center of masses are still works, but those numbers were wrong. Any other questions about that? Okay, so this discrete formula also works with subtraction. So you can remove material. So let me do an example. So how about a shape like this? So you have a square plate with a circle removed. Here's the center of the square. The material is the shaded part. This is 1 meter by 1 meter. We'll put the coordinate system here. And we want to know what's the center of mass of this shape. We can treat the square as body 1, the removed circle as body 2, and then the position vector of the center of mass times the total mass of the shape is going to be the mass of 1 times its center of mass minus the mass of 2 times its center of mass. So piece 1, I need to give you a density and a thickness. So let's say the thickness is 0.1 meters, and the density is 5,000 kilograms per cubic meter. Then the mass of the square, so if this was a complete square, the mass would be 500 kilograms. So 1 times 1 times 0.1 times the density. The centroid, the position of the centroid, what would that be for the square? Yeah, it would be right at the origin, so 0, 0. Piece 2, the mass is, so this has to have a radius of 0.25. So we have pi times 0.25 squared times the thickness times the density. So the mass of that removed shape is 98.17. What's the position vector of the center of mass of that circle? Yep. So now combine that into the formula. So what's the total mass of this object? Yeah, right. So 401.825 times the position vector of the center of mass is equal to 500 times 0, 0 minus 98.17 times 0.25, 0. And you get a position vector for the center of mass that's equal to negative 0.0610. So it's on this line of symmetry and just a little bit over towards the material. Any questions on that one? Okay. In talking about Newton's second law, the thing that's important to us is the acceleration of the center of mass. So here's another thing to notice about this. The integral and the discrete formulas for the center of mass give similar integral and discrete formulas for the velocity vector and the acceleration vector of the center of mass. So remember, this is the formula, the definition of the center of mass is total mass times the position vector is equal to the integral over the mass times integral of the position vector times the increment in mass. This integral doesn't have anything to do with time. So you can just differentiate both of these with respect to time. The masses don't have any time dependence, and so you get m total times the velocity of the center of mass is equal to the integral over the mass of the velocity times the increment in mass. And same thing with the acceleration. The total mass times the acceleration of the center of mass is equal to the integral over the mass of the acceleration vector, dm. And the discrete formulas look just the same. The total mass times the velocity of the center of mass is equal to the sum over all the individual pieces of the mass of the individual piece times the velocity of the center of mass of the individual piece. And same with the acceleration. Okay, so here's an example I'd like you to work on. Say that you have two objects, and they're both moving. Say this is 1 and this is 2. The mass of 1 is 10 kilograms. And the position of the center of mass of 1 is defined by the function t 4t. The mass of object 2 is 5 kilograms. And the position of the center of mass of 2 is equal to negative 3t squared, negative 0.5t. And the question is, what are the velocity of the center of mass of the system and the acceleration of the center of mass of the system? Okay, so velocity of the center of mass of 1 is 1.4. Acceleration of the center of mass of 1 is 0, 0. Velocity of the center of mass of 2 is negative 6t, negative 0.5. Acceleration of the center of mass of 2 is negative 6, 0. So 15 times the velocity vector of the center of mass is equal to 10 times 1/4 plus 5 times, negative 6t, negative 0.5. And so, what do you get there? Velocity of the center of mass is equal to 0.667 times 1/4 plus 0.333 times negative 6t, negative 0.5. So you get a function of time for that one. What did you get for the numbers there? I didn't want those numbers anyways. I use reverse psychology so you wouldn't give them to me. And then the acceleration, 15 times the acceleration of the center of mass. What? Is the acceleration? Okay. So, yeah, so 10 times 0, 0 plus 5 times negative 6, 0. So this one, the acceleration of the center of mass is equal to negative 0.50. Any questions about that? These are easy calculations, but you'll have to do them in like almost every problem. Yes, thank you. Okay, now any questions? Dang. Okay, now any questions? Okay. Okay, so the next thing that we need to talk about is angular kinematics, angular kinematic quantities. Angular velocity and angular acceleration. And I'll talk about it first in 2D and then describe the changes that are going on in 3D. So consider a rotating rigid body. So say that it starts in this position and rotates to this position. Say that it has a fixed axis somewhere. And then draw a line that's fixed on this object. It doesn't matter where that object is. When it rotates, that line will rotate like that. and it'll make an angle theta. And no matter where you draw that line, that angle theta is going to be the same thing, and it's going to have the same direction. It's either going to be clockwise or counterclockwise. If our coordinate system is like this, that rotation is, so it rotates an angle theta, where counterclockwise is positive, about the z-axis. So counterclockwise positive, notice, the reason that counterclockwise is always positive is because that's what obeys the right-hand rule about the z-axis. So if this rotation happens, if this rotation occurs over a time interval delta t, then you can define the limit as delta t goes to 0 of that change in theta. I guess I'll call that change in theta over delta t as the time derivative. And that's what we're going to call omega, the angular velocity. And here's something important about the angular velocity and about all these angular kinematic quantities. Since that angle, change in theta, is going to be the same no matter where you draw that line, no matter where you draw it on the body, the angular velocity is a property of the entire body. Now, for this to be true, it has to be a rigid body. But notice that's not the case with velocity, with linear velocity. If this thing is rotating, then at this instant, think of the velocity at the point on this side of the axis of rotation. That's going to have a downward velocity. The point over here is going to have an upward velocity vector if this thing's rotating. So velocity isn't like, if you're asked for the velocity of a rotating body, you're going to need to know which point you want the velocity for. That's not true of angular velocity. Okay, angular velocity is true for the whole thing. Okay, so 2D versus 3D. Yeah. So omega is really always happening in 3D, right? I mean, even in our 2D problems, we're just ignoring some directions. So omega is really a vector. With a direction along the instantaneous axis of rotation. So during any rotation, at any instant, there is a single axis the thing is rotating around. Okay, the thing can be flipping through the air, however, but instantaneously, there's always a single axis the thing's rotating around. And which direction on that axis the angular velocity vector goes is determined by the right-hand rule. Okay, so the direction along the axis is determined by the right-hand rule. If you need to express 2D angular velocities as vectors for calculations, and when we get to the equations for this stuff, you'll see why you might have to do that. It's always along the z-axis. So the angular velocity vector is always going to be 0, 0, omega. Okay, so let's think about a couple examples. So imagine for all these, the magnitude of the angular velocity is 1 radian per second. And the question is, what's the angular velocity vector? So for the first one, say it goes around the back, over the front, rotating like this. For the second one, say it goes like that. And for the third one, if this angle's 45 degrees, say it goes like that. Okay. So see if you can figure out what those angular velocity vectors are and compare your answers to each other. For the love of God today, compare your answers to each other, people. So, okay. I can do better. Okay, so this one, that's the direction the right-hand rule says. So what's this vector going to be? 1, 0, 0, yep. For this one, well, that's much worse. So this one is 0, negative 1, 0. And what's this one? Also, this one only has 3 fingers. Each one gets worse. I'm glad I only did 3 examples. So this one is in negative 45 degree direction. So, negative cosine of 45. What? Yeah, yeah. Okay, so that's the definition of the angular velocity. If you take the derivative with respect to time of the angular velocity, you get the angular acceleration. That's alpha, is that Greek letter. This is the one that's going to be the most important for us because this is the one that's in rotational Newton's second law. This is a vector also. It has SI units of radians per second squared. And just like the angular velocity, it's important to remember that this is a quantity, this is a property of the entire rigid body at an instant. That's not true. Just like it wasn't true of the linear velocity, it's not true of the linear acceleration. Okay? But these angular properties are different. 2D versus 3D. Since omega is a vector that can change directions, it can only change directions if you're talking about 3 dimensions. If in 2 dimensions, it's always in the z direction. Then in 3D, the angular acceleration and the angular velocity aren't always parallel. In 2D, they are, though. And they're always parallel to the z-axis. And that's why, because in 2D, the angular velocity and angular acceleration are always in the same direction. That's why a lot of times you see those written as scalars, and you're used to doing calculations with those as scalars. But they're not, they're vectors. They're just always pointed the same direction, so we kind of leave off that extra information. Okay. In 3D, though, you need that information. Once you know the angular velocity vector and angular acceleration vector of a rigid body. And by the way, so I said that some stuff, these are properties of the whole body as long as this is a rigid body. If it's not a rigid body, these aren't even really defined properties. These are properties of the whole body or nothing at all. So if you want to talk about angular quantities for something that isn't rigid, you need to mathematically treat that thing as a bunch of rigid parts, okay? There's no such thing as these angular quantities if you have just a lump of pudding, okay? But for a rigid body, once you know the angular velocity and angular acceleration, you can use the two equations I'm going to give you to find the velocity vector and acceleration vector at any point on the body. And these equations are the velocity at a point is equal to the angular velocity crossed with a vector r, and the acceleration of a point on the body is equal to the angular acceleration crossed with r plus the angular velocity crossed with the quantity angular velocity cross r. In both of these, r is a vector from the axis of rotation to the desired point. And by the way, these are vector versions of equations that you've definitely had before. I don't know, did you talk about, like in circular motion in physics, did you talk about these with this vector form? Okay. So this is a vector form of omega times the radius, gives you like a scalar speed. This is a tangential acceleration. And this is a centripetal acceleration. If the axis of rotation isn't fixed, and actually, if this axis of rotation, let's call the axis of rotation A, okay, isn't fixed, combine the two equations above with the relative motion equations. So the velocity of your desired point relative to the origin is equal to the velocity of your point relative to that axis of rotation point. Plus the velocity of A relative to the origin. And same thing with the acceleration. Acceleration of P relative to O is equal to acceleration of P relative to A plus acceleration of A relative to O. Okay, so let me do one example. Any questions about that? Yep.
With that R vector, is that the nearest point on the axis of rotation or from the origin?
Okay, so actually, this A vector, So that would be so that axis of rotation, that actually needs to be a point that it's rotating about. Yeah. So let's call that an about point. Okay, so say that you have some arbitrary object, and here's its center of mass. There's your coordinate system. Here's your point P. And say that at this instant, omega is -6 radians per second, and alpha is +14 radians per second. What? Squared, yeah. Right. And say that the velocity vector of the center of mass is 10 meters per second, 5 meters per second. And the acceleration of the center of mass is -8 meters per second squared, 4 meters per second squared. And this is, a lot of times, this is how it's going to come about. You're going to know something about the center of mass. Often you're going to know the acceleration of the center of mass because that's what you're going to get from Newton's second law, right? And then you're going to have to use the relative motion equations. Once you figure out the rotation, treat it as a rotation about the center of mass, and use the relative motion equations to get the total acceleration. Okay, so what's the velocity vector at P, and what's the acceleration vector at P? By the way, I think this is important to notice. So these equations are used for this and this. Okay, so the velocity of P relative to the center of mass is 0, 0, -6. That's the angular velocity, crossed with the r vector. Oh, and I need to give you this distance. Say this distance is 0.3 meters. Crossed with that r vector, which is -0.300. And that gives you 0, +1.80. And then the velocity of P, which you can think of as the velocity of P relative to a fixed origin, is 0, 1.80 plus the velocity of the center of mass relative to the origin. So 10, 5, and then 0 if we're still using 3D vectors. And so you get 10, 6.80. So this is the vector velocity of the center of mass, velocity of p relative to the center of mass. And this is the vector velocity of the center of mass relative to your fixed origin. Okay, let's do the acceleration one at the start of next class. Any questions about that? Okay.